I'm sure a lot of you have used a chatbot, right? And you've used a chatbot built by different companies. Maybe you used a chatbot at Swiggy, maybe you used a chatbot at Zomato. Basically, you've used a chatbot to give you answers to certain questions whenever you have used an AI bot, right? For example, if an order fails on Swiggy, what happens is you're exposed to a chatbot where that chatbot answers questions that you have, tries to answer it to the best of the chatbot's ability. Sometimes it's a bit frustrating, sometimes it's okay, sometimes it's not. But in either case, that chatbot is powered by an LLM, right? But behind that, and a lot of times you understand that a chatbot can give you incorrect answers. They can give you completely wrong answers, right? The reason because of which a chatbot gives you incorrect answers is not because the inherent model that was being used at that chatbot was incorrect, right? The problem is that a model can only be trained on a finite set of data, and sometimes you have data that is inherently specific to your use case. For example, let's say Swiggy's refund policy. Let's say Amazon's refund policy, right? Now you can integrate a lot of LLMs, you can integrate a lot of LLMs on top of it, but every single time it would be very difficult for an LLM to get this context based on its training alone. And that is what RAG is, and that is where we come with RAG, right? By the end of this next 45 minutes or so, you will know exactly what RAG stands for, when to decide to reach for RAG, and most importantly, what are the product decisions? What are the decisions that a product manager is expected to take when it comes to RAG? Right? So we're not going to talk about engineering decisions, of course. We're going to talk about the product decisions that you are supposed to take when it comes to RAG, right? So that is what this community live is all about. And let's get started. Now, like I said, fundamentally, the biggest problem with only using a large language model, such as your OpenAI's models, GPT-4o, Anthropic's models, Claude, whatever, is it's even if it's incredibly well trained, incredibly well read, but has probably the knowledge of the entire internet, but then there are always certain things that the model cannot see, right? There is certain data that the brain, the LLM model, the brain is unable to see. The model is smart, they can reason, they can write, explain, sometimes generate images out of that explanation, and all of that. But there are three things that are usually locked out of that model, right? And that is majorly the reason why RAG exists. What are these three things? First is that they know everything on the public internet, but not on things about your company, right? So things like your company's refund policy, things like, let's say, your company's leave policy. So inherent internal decisions, internal policies, internal frameworks that your company uses are unknown to any model, any AI model being run, right? Second is that they are smart, right? They can, of course, reason, but every model is going to have a cutoff date for their knowledge. So anything recent is invisible to them. Now, you may ask that, hey, if I ask Claude today's news, it's going to be able to give me that news. Fair. But it's actually not the part of the training data of that model. What happens is the model fetches the news live based on web search on the day and then runs its model on top of it. The fundamental problem with this is that because the data is being fetched live and run on, the reasoning is going to be slightly weaker, especially because of the cutoff date from there. And then number three, the bigger problem or the biggest problem around LLMs is hallucination. Now, fundamentally speaking, when a model is incorrect, right? When a model does not know the answer to your question, when a model does not have the answer to your question, they are not fundamentally trained to say, I don't know, right? What do I mean by that? A model is always fundamentally trained to work on creating answers for you. So while the model can give you an answer that, hey, maybe I don't know this for sure, but it's always trained to give you an alternative. So it's probably going to give you an alternative that usually this is the refund policy. Usually this is what we do. And of course, if it's exposed to an end customer, the end customer can take that as a truth, and that's a big problem, right? And because their model itself does not know that it does not know what is going on, it's going to sound very confident, right? We call that hallucination, and that's a really big problem. And essentially, that is where a model will give you incorrect data, incorrect numbers, and it'll give you extremely confidently, right? Today, what we're going to talk about is the use cases that RAG fixes, right? These are the three use cases because of which an LLM is not enough. Today, we are going to talk about why and how RAG fixes it, right? Now, let's understand what's going on, and let me try and give you an analogy that can help you understand this, right? Now, fundamentally, you should treat RAG as an open book exam, right? Now, picture two versions of an exam. There is a closed book exam where you're running purely on your memory, right? And if you did not memorize a certain concept, you are going to be guessing, right? Open book is where you have a book right next to you, so the same brain. But now, when the question comes up, you can flip to the right section, read what's relevant, answer what's actually in front of you. That is called as RAG, or retrieval augmented generation. That's the fundamental idea. You're not making the model smarter. You're not changing anything about the model's training. You're not making the model, know more things. All you're doing is you're giving a model an open book, which it can open wherever required and use that to give you answers, right? So the reasoning, the logical a part of it, the whole thing, that is still the model's job. But you, by the implementation of RAG, are now able to control the facts given to the model. Keep this picture in your head all time, right? Whenever you're thinking about RAG as a fundamental concept, or even when you're evaluating when to do RAG in a product and when to not, keep this picture in your head, right? Because RAG essentially is an open book exam. If it was not there, you would have to memorize the entire book. If it was there, you can just memorize the logic or the fundamental reasoning that is there. And then whatever facts you need from the book, you can just pick it and add on top of that reasoning. That is exactly how a RAG implementation works, right? Now, before we jump into specifics of RAG, there are two fixes that you can think of, or there are two fixes that you can say and maybe talk about and say that, hey, why don't we use this, right? Why are we only choosing RAG to do this? And that is what we're going to talk about before we talk about RAG. Now, there are two shortcuts that people reach for whenever they hit problems like this, which is not having access to your data, hallucinating, not having latest data, and so on and so forth. What are these? First is that they try to fine tune the model, right? What fine tuning means? Fine tuning means is that you give the model your data and you train the model on your data sets. Remember, in RAG, we are not training the model on any data set. In RAG, what we are doing is we are just adding a layer of knowledge on top of the model. For example, think of it as basically when you're doing RAG, you're just adding a more detailed prompt with a knowledge base on top of whatever is already there. But one thing that a lot of people say or argue is that, hey, why don't you change the data set in the model? Now, while that sounds good, fine tuning is very expensive, right? Training a LLM data set is extremely expensive and it's extremely slow as well. So the moment you're retraining a model and you're going with a fine tuning route, yes, you can actually solve the problems that I mentioned, but it's going to cost a lot of money and it's going to take a lot of time. And because these changes happen weekly, right? You remember, we did say the news that is available today. Because these changes happen daily, weekly, it's very difficult for you to keep in sync with whatever is going on. Second, a lot of people say that, hey, why can't you use a huge context window, right? Which is, why can't you paste everything that you know in the prompt? And that is where the LLM will take whatever it's needed from the prompt and go ahead and do it. Of course, this is also right. It fixes the problem, but it makes every query expensive. And of course, slower, because now the LLM has a lot of data to go through, and that is where it's not going to be able to solve it, or it's not going to be able to give you a good answer, right? Now, because of this, right, both of these methods, for any organization that's trying to be cautious with the money that they spend, for any organization that's trying to build a faster model, RAG still exists, right? Now, you would hear myths a wrong side saying, hey, RAG is dead. And now we've got the context window of 1 million context and so on and so forth. And that is going to replace RAG. But actually, you both are wrong, right? Because the cost and quality of fine tuning and a large context window is always going to be inferior to what a RAG implementation can offer. First, because RAG is cheap, it's extremely quick to implement, and it does the job really, really well. So when people say that, hey, RAG is no more useful because the context windows have become really large, they're right. But large context windows also mean large costs. And that is something that not every company is going to be able to use. Right. Now, enough fundamentals. Let's start diving into what RAG essentially means. Right. Now, RAG stands for, RAG rather, stands for Retrieval Augmented Generation. Right. Now, let me break down this in simple English. Retrieval essentially means to fetch something, right? To get something back, right? It's not, retrieval means that when do you retrieve something, right? When you retrieve something, when you give it to someone, right? So if I can just open a whiteboard, I hope you are able to see the whiteboard as well. I can just create a new board here and I'll just call it RAG explained, right? So I'm going to just put three blocks here. What are these three blocks? The first one I'm going to say retrieval, right? Now, fundamentally speaking, the one thing that you have to understand with retrieval is that in English, the word retrieval means that you're getting something back that you gave in the first place, right? So you have to remember that when you say, when I say, hey, I'm going to retrieve a document, when I'm saying, hey, I'm going to retrieve a ticket, what I mean is that I had given the ticket to someone, I had given the document to someone, I'm going to get it back here, which means that the first fundamental piece that you have to understand is retrieval in RAG, or retrieval augmented generation, stands for getting something back that you gave in the first place. Talk a little more on that in a bit. Now, what's the second? The second is called augmented, right? Now, what does augmented mean, right? If I go and just Google and say augment meaning, augment is a verb that makes something greater or more effective by adding to it, right? So essentially, what does augment mean? Augment means that when you add something to on top of an existing piece and make it better, right? So I'm just going to copy this definition so that we remember this as well. Thank you, Google, for giving us a good definition, but I'm just going to put it here, right? So retrieval means getting something back. Augmentation means, I'll just put it here. It just means to make something greater, larger, or more effective by adding to it. Which means that here the fundamental principle that we are seeing is that you are going to retrieve something. We'll talk about what this something is. Then you are going to augment that something and make it better, right? So far we've understood that, okay, the fact is that we're going to retrieve something and then we are going to make it better through augmenting it. We'll talk about what that is. Now, the third term is generation, which basically means generating output, right? So generation in an LLM context is to create the output for by the LLM. Now, this means the output that you see on your GPT, the output that you see on your Claude's models, whatever, right? So the output generated is generation, right? So sequentially speaking, if you look at retrieval augmented generation, what it means is generation is getting augmented, right? Because if you see retrieval augmented generation, so this generation is getting augmented. How? It is getting augmented by retrieval, right? So I'll repeat that again. What here is happening fundamentally is going from bottom to up, is generation is being augmented, which is means that it's being improved via retrieval, right? And that fundamentally is what RAG means, right? Very simple English, very simple broken down. This is what fundamentally RAG means, right? So we need to find a way by which we can improve the answer that a GPT or an Opus gives us. And the way we are going to do it, or the way we are going to augment the answer here or make it better, is via something called as retrieval. Now, this basically means we have to understand each of these three pieces one by one and use that to our understanding. Let's do that. Very simple to understand this. Let's try and understand what retrieval means, right? Now, remember, when we talked about the reasons why RAG exists, one of the fundamental pieces there was the fact that LLMs don't have the knowledge of certain concepts directly. So an LLM does not know, for example, the refund policy of your company. The LLM does not know, for example, the employer policy. The LLM does not know, for example, let's say if there is an internal document or internal PRD that you've written, an LLM does not know that, right? And that is what we are trying to fix here. So fundamentally, what happens in retrieval augmented generation is your data, the data that you have, the fundamentals that you have, they are stored somewhere. Then, whenever that data is required, they are retrieved, and then that retrieval or that retrieved data is used to improve the generated outcome, right? I'll explain it very simply. Let's assume that we are using ChatGPT, right? And here we are saying, hey, what is the refund policy for Amazon? Right? Now you ask this question, let's assume to ChatGPT directly, and ChatGPT gave you an answer based on web search or wherever, where to make it simple, we're just going to say refund policy for ChatGPT, sorry, for ChatGPT is 7 days. Sorry, refund policy for Amazon is 7 days, right? That is what that is what you were told, right? So the refund policy for Amazon is 7 days. Now, this is happening by this. Now, for example, some executive decides on Amazon someday that, hey, no, the 7 days is not right. We're going to change it to 10 days. Now, the model, the LLM here, which is uh, right here, let's say the LLM. Now we're going to name some LLM. So let's say GPT 5.5, uh, Opus 4.8, let's say Fable 5, whatever those models are, right? Now they are being answered this question. They gave you this answer because this is what their knowledge was. Now, today, someone has changed this policy, or someone at Amazon has changed this policy, which means that there is no way that this guy can know it unless, it's trained on that later. So in retrieval augmented generation, what we do is we just add something called as a knowledge base on top of this, right? Which has all details of Amazon policies, right? So it has details of purchase policies, refund policies, every single policy that Amazon has. There is a knowledge base that is created and is stored somewhere. Now, whenever this question is now asked to Amazon, what happens first is retrieval of relevant information happens, right? So the first thing that happens is retrieval of relevant information happens from this policy, right? Here, as you can see, the question was around refund policies. So that is why the answer would be the relevant data on refund policies would be fetched, right? Perfect. Now what happens is this relevant detail that you have fetched from here, that relevant detail gets added to the original question, right? So what happens is, let's assume that there were 10 lines of data that came here that were relevant. Now those 10 lines get added. Actually, I'll put it back here. Yeah. Those 10 lines get added on top of the question that was asked as a prompt, and then the LLM is supposed to run on it, right? So just repeating it again, it starts with the question. Now, what happens first is the retrieval of information happens. Then, based on the relevant information is copy pasted and added on top of the refund policy, and then the answer is generated. Now, this step here, this step, if you can see this step is called retrieval. This step is called augmentation. And this arrow, the last one, this arrow is called generation, right? So you're retrieving the information in the step one. Then the relevant information that you have got, you're using that to augment and improve your response. And then once you've got that, you're then going to generate the answer, right? So essentially what happens is the data that gets added here, that just gets, or the knowledge base that is relevant here, that just gets added in the prompt itself of whatever was originally asked. So if, for example, this was just, 6 or 7 words of prompt, but now let's assume that because of this, here when you once you figured out the right knowledge base or whatever was relevant, let's assume that this was 100 words, right? So now the prompt that will go to the LLM model to generate would be, let me just do this, yeah, would be what is the refund policy for Amazon plus the 100 words from retrieval and augmentation, right? So what would happen is you would, you know, these two would go together instead of, yeah, this is what would happen, right? So instead, you go ahead and say that, hey, this 100 words that you have from here, they get added to the refund policy, and then both of them together go to the LLM. The LLM doesn't know it, right? The LLM has no way to understand whether this is the right way to do it or not. For the LLM, everything is the same. They don't really have a way by which it can understand, what Amazon is and all of that. It just understands whatever it's trained on. So now, because of this, what has happened is you've got refund policy, you've got the relevant document, and anytime you make this change in the document, this entire thing is going to be fine. So all Amazon needs to do is create this knowledge base, create this pipeline that we saw using arrows, and that's it. Whenever you change it here, every time now this gets generated for someone who has access to this knowledge base will always give you the right answer. So when Amazon makes a chatbot, they don't need to change anything. They just need to have someone who needs to maintain this entire knowledge base. Right. Now, of course, the main piece of understanding RAG is about understanding these arrows, right? We'll take them one by one. First, we'll understand retrieval. Then we'll understand augmentation, and generation is, of course, something that you already know, which is, you already put prompts on LLMs and then prompts generate answers. So let's try and deep dive into retrieval first. I'll just go back into full screen and let's talk about this. Now, this is the one that I want you to actually remember. The retrieval pipeline, right, of what happens to retrieve cannot happen without something called as ingestion, right? What do I mean by this? What I mean by this is that, hey, this retrieval is happening here. This is fine. But this knowledge base has to be ingested somewhere, right? Essentially, what I'm talking about is that this knowledge base has to be created and stored, right? Only when this knowledge base is created and stored would you actually have something, right? Otherwise, why would you have this work out? Otherwise, it will be a problem, right? So only when you have the knowledge base created, stored properly, and it's called chunked, but we'll talk about that in a bit as well. But basically, what I'm trying to say is that this knowledge base has to be created. You cannot, that's the first fundamental concept that you need to understand. Now, second thing that you have to understand is once this knowledge base is created, then relevant information has to be extracted, right? So there are two pieces of this retrieval thing, right? What are those two pieces? The two pieces are very simple. I'll just put it here and I'll say retrieval, and I'm going to say the two pieces here is ingestion, which is the process of creating this knowledge base in a way in which it's extremely fast to get information from that knowledge base. And second is extraction, right? Which is basically what is the exact relevant piece that I want, and I want to take it. Now let's see how this happens. The first part of ingestion, right? I already told you each RAG system has retrieval system has two halves, ingestion and extraction. You can call it in multiple places. I mean, some places you call it indexing and retrieval, other places it's ingestion, extraction. But basically, concept wise, one piece is creating the data ready, another piece is pulling the data whenever required. So there are two halves to this to the RAG retrieval parts. The first one is ingestion or indexing. Now this is done once. Of course, you don't need to do this ingestion again and again unless your document changes. If your document changes, of course, you would need to do it, but this is a one-time usually activity and it's done offline. Essentially, what you do is you take your document. So let's assume there's a refund policy from Amazon. You take your document, you break it down into smaller pieces in something called as chunking, right? So you break it down into smaller pieces and something called as chunking. And then using those chunks, you basically make sure that each chunk has, a footprint, a place by which I can find that chunk very, very easily. And then you store it, right? So basically the preparation of knowledge base is very simple. What happens in this preparation, as you can see, you take your documents, you break them out down into smaller chunks. Now, remember that the main aim to get these documents is to retrieve them back, right? That's why they're getting stored, which is why if you just store them blindly as a list of items one by one, what will essentially happen is you run the risk of making your system slow, right? Because you would have multiple things in the system, you run the risk of making it slow. So instead, what you do is you do something called as embedding, which I'll talk about briefly in a bit, what that means, which basically is the way by which you can give each small chunk that you created its own location, right? And when I say location, I actually mean location. Each small chunk, an exact location where it can be stored. Once each location, each chunk has got its location and that location is created, then you go ahead and put them down into something called as a vector store, which is a database, but a database that can store your chunks with their location and not alone. So once again, document creation, chunking, embedding, storing into vector database. Most of this is done by engineers. You don't have to worry about knowing this, but you do have to understand when someone says that, hey, I'm embedding, or what embedding we should use and how we should embed it, or what is the chunking strategy. All of that is a product decision. We'll come to that in a bit, but we'll complete the other half of this pipeline as well. Now, the second lane is retrieval, right? Now that my document is chunked and available in small pieces, I need to retrieve the right piece every time. So this happens live on every single question that you ask. Whenever a user has asked, for example, the question on refund policy, what happens is you find the most relevant chunk, right? You find the most relevant embedding. So when I say embedding, I mean the chunk with their location, right? Together they are called embedding, right? So you find the most relevant chunk that is required towards this, use that and rank all of them, right? I'll talk about what that means. Use all the chunks that you've gotten, rank all of them, add data to the prompt, and then answer. Let me repeat it again. When retrieval happens, what happens is the user asks the question, which is, what is the refund policy on Amazon? Then what happens is the question is stored in the same embedding that your original chunk was stored in. Now, why is that happening? This step is happening so that both your chunked piece of information from your knowledge base and the question are now living in the same ecosystem, right? Let's assume that the chunking happened on the term refund policy, right? The chunk has a heading refund policy, which basically means that everything around the refund policy is in that chunk. Now, unless this question is also broken down into an embedding and stored with details around refund policies, how would your pipeline know that, hey, both of these chunks are actually relevant and they should be matched together in this particular query? Right? So that is what happens once the question is asked. The question goes and follows the same embedding model that the chunking while ingestion was used, and because of that, now it's in the same universe. There is a search. Search results the best chunks, maybe 10, 15, 20, 30, whatever. Then there is a ranking, which means that out of the 20, you don't want to send all your chunks. You will send maybe the top two, top three, basically top K, and then use that to add to the prompt of the user that was originally there and answer it. And the LLM then answers the question correctly, right? I'll repeat it again. In fact, maybe just let me take a quick screenshot of it and explain it with the example there, right? So here, the docs, this was what? This was the document for your refund policy. Chunking, we'll deep dive into what chunking is and why is it a product decision in a bit. This is something which is where you break down your document into smaller pieces and store all of them. Embedding is where you store all your data with a location, right? A vector location, and vector store is the store in which you store it, right? Now, when the question, which is what was the refund policy for Amazon, happens, you have to find the relevant chunk from related to this question, which means that you have to either bring the ingestion to the same universe as retrieval, or you need to take the question to the same universe as the indexing. So here the latter happens, where this question itself, right, what is the refund policy for Amazon, this is embedded using the same logic that your chunks were embedded in. Once that happens, both these chunks are very close to each other because they are vectory. I mean, they have a location, right? And the location is based on the context, right? So if one chunk talks about refund policy and a question is around refund policy, you can bet that both of them will be embedded very close to each other. So now, once that happens, that embedding is searched. You find the top results from that embedding, you add it to the prompt like we saw here, and then you generate the answer, right? And that is where you have to understand how important or how technical it is to get the logic of each of this, right? Each of this step has a product manager's involvement, right? It's not like these are all isolated from each other. They have the involvement of a product manager as well. Of course, some of them more, some of them less, but every problem that you would face, or every, for example, if your manager or someone will tell you to improve the quality of the AI bot or the chat bot, that can drill itself down to one of these things not being done well. The chunking may be bad, the embedding might be bad, the vector store might not be fast enough, the questions embedding might be bad, the search might have a problem, the top K might not be selected properly, and so on and so forth, right? So that is how fundamentally RAG works. Now, let's try and understand the difficult concepts within this, and we'll start with the first one, which is called as chunking, right? Now, what is chunking? Chunking essentially just means how do you cut your documents into small pieces and store them in a way where you can find them later, right? It's pretty boring, to be very honest. If you look at what it fundamentally means, it's just that if I've got 100 pages of words, how can I make them different versions? Now, there are four ways of chunking. What are those? First is fixed size. So I say that I've got 200 words in this document, 5 words is a chunk. Now, understood, you can easily understand that that's not a right way of breaking down your documents, because sometimes the document will get broken at sometimes it will get broken at in between the words, sometimes it will get broken in a space, whatever it is, right? So fixed size chunking is simple, but it will cut your sentences every few mid thought, right? Because you would have a sentence that is just going to get cut mid thought. Simple, but not really a great way to chunk it, because it's going to not have great retrieval, because the pieces that will get retrieved would probably all be a little broken. Right. Now, the next and the most common one, or the most important one, is semantic, where you cut chunking or you cut your data based on the topic. So when the topic is changing from refund policy to return policy, you have two different chunks. When the topic changes from return policy on Amazon to customer behavior document, the chunk changes. So semantic is where basically you change or you chunk based on what's going on in the document, instead of chunking it based on your own fixed mind or whatever, right? Now, of course, you would require some LLM model to do it, because you would not be able to understand where it shifts, but it's a fairly straightforward code from there. Third is document aware. So where basically the document itself is created in a way where there is a heading, there is a section, there is a divider, there is a different page. So the document aware chunking is basically saying that, hey, I have created the document in a way that everything is chunked in the document itself. I've created, all the breakdowns, and then you can use it. Document aware is also manual chunking, because in this you will have to create the document in a way that it's chunked easily. And finally is hierarchical, where it's pretty interesting in terms of how hierarchical chunking works, where what happens is you have a small, precise chunk to find the answer, but a larger, bigger parent chunk to find the context, right? So if I'm talking about refund policies, first there will be a bigger chunk for policies, And then within policies, there will be smaller chunks for refund, return, customer behavior, employee behavior, whatever, whatever. Right? So hierarchical is important. And as a product manager, it's your decision to understand which chunking are you going to use. Are you going to spend time and make a document that is so good that you're going to use that? Or are you going to spend time on hierarchical chunking and try to create a way by which you have a big concept for context and then a smaller individual one? Are you going to implement semantic which changes based on what's going on, or are you going to do a fixed size, right? So that is basically how you have to understand it, right? And that is what chunking is all about. Now, I prepared a quick demo for you as well, just to understand how it works. So let's, these are, for example, just 1 minute. Yeah, this is the one. So what happens here? This is a small demo to understand keyword versus semantic. So what has happened here is I've created some chunks. So as you can see, there is a refund chunk, original, whatever is there, and all of that. So what I've done is, if you create that document in a fixed size, you would just have 8 words for each chunk. If it's semantic, it's going to break that document down into pieces where refunds, then approved refunds, and all of that. If you go ahead and document aware, it's just going to follow the exact document that I created, right? So that's basically how it works. Just to tell you about keyword versus semantic. So basically what happens is, semantic is, like I said, about context. So here, for example, if the question is around who is iPhone maker's boss, you can talk about Tata Motors because it just has the word maker. But semantic search is going to find things around Apple, leader, and all of that to do it, right? More on this in a little bit when we do a demo of this entire thing, right? But essentially, these are the 4 ways in which you can chunk data or store it. Now, almost always you would never require to implement the chunk yourself. Always the chunking will be implemented by someone else, mostly the engineer. All you would have to do is you'll have to just sit on it and understand what's going on and build it out from there, right? So that is basically how chunking would work, or that is basically how the entire flow of chunking would work out, right? Now, what is the product manager's decision in most cases here? The product manager's decision is which kind of chunking to choose, right? That is where you're going to go about it, right? Now, let's move forward and understand the next piece of it, which is embedding. Right now that I've understood that, hey, this is the chunk that I have and this is the chunk that I have created, I need to store it. And this is where it's a little complicated. Right now, let's assume a standard database. Right, let's assume that there is a database. That database has tables. It's a database for your customer. It has a table for customer name, phone number, email, etc, 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 right? All of that, all of those details are there in the table. Now, very straightforward way to store it, right? You just store row 1, customer name 1, customer name 2, customer name 3, row 2, customer name 2, customer name 3, customer name 4, right? Very simple. You One row is for one customer and it keeps adding on top of it, right? This was a standard way. But then the main problem with this was that if this was the way in which your data storage was implemented when you are doing RAG, there will be a fundamental problem. What would be the fundamental problem? The fundamental problem when you implement this via something called via RAG is the retrieval will become very, very long. Because if you, let's assume, store chunks and you just store chunks one by one, right? The pipeline will have to now go ahead and compare each chunk one by one with the embedding that was created out of the question. So if the question was broken down into, let's say, 2 3 words, you would have to compare them again and again. So essentially, storing them normally does not work, right? Why? Because here the variables are that the question has something, the answers in the knowledge base have other chunks. I have to put them both into the same ecosystem and then compare it. If I just store the answers as a standard database one by one, it's going to take me a lot of time to compare it with again and again. And that's going to defeat the overall purpose of implementing RAG, which is where we come to embeddings. Right now, this is where, of course, like I said, it's a little confusing for people. A lot of people, trip up here and try, but I'll try to make it as simple as possible. Now, fundamentally speaking, A computer does not understand text, they understand only numbers. So what we do is we take every chunk, right? The chunk that we just saw here, right? If you see that artifact that I showed here, you see these are all the chunks that were here, right? This was all the chunks. 499, 9 p.m. IST. Of course, this was when I do semantic. These are all eventual chunks, right? One by one, right? So now what happens is each of these chunks are stored as numbers. But the trick is that you store them in a way that similar things get similar numbers, which means that they sit close to each other. For example, if you're chunking two words and one is about a dog and as another is about a puppy, they are going to get numbers to store them into a database. But the fundamental difference will be that these numbers will be close to each other, almost like the coordinates that we studied in maths when we were studying Cartesian coordinates, right? At that time, what used to happen? We used to study, and similar points with similar geographical location used to be plotted close to each other. It's the same logic here, where each chunk is given a number, and if the two chunks have if the two chunks have a similar meaning or a similar context, they are stored closer to each other, right? So invoice, refund, policy, all of this will be stored closer to each other. That is why whenever retrieval happens, it can happen really fast, because now your question was broken into refund and the question was also plotted in this graph itself. There was an ingestion that was done on refund again, where it was plotted again, which is basically, you know that now these two are very close. It's really quick for the pipeline that you build to map them, and you get your answer, right? So I'll repeat it again. The way to store chunks is by storing them very smartly, compare them into a number. Now, this number is not like a 1, 2, 3. This is like a long number, because what happens is you store similar words at similar places, and then each of this interaction is called an embedding, right? Which means that similar things with similar numbers sit close to each other in this space. So whenever you get a question on dog, and then you break down and embed the question on dog, you know that that would come somewhere here, and then you know the answer or the knowledge base. The chunks with dog are also going to be nearby, so the search, you would do a quick search around it, and that is how you get it. This entire process is called as semantic searching, right? Which is basically finding the nearest neighbors to the question and creating a way by which all your answers come to you semantically, right? You're finding matches by their meaning and not by the word matching. If you did word matching like you would do in a standard database, it would be a lot of time, right? Which is why the latency will be high and the performance would be bad. But you don't want to do that, which is why you're going to go ahead and do something like this, right? That is how you need to understand, or that is how you need to do this. Now, to store this data or to store these embeddings, your standard SQL and standard databases don't work, which is why we use something called as vector databases. Now, why are they called vector databases? You've understood very clearly, because here we are always storing data in locations. So we are not storing data everywhere else. You're storing data in locations, which means that you're trying to understand the exact location and finding it. Now, understand that a computer does not understand what a dog or puppy means. But for a computer, a dog, the location of a dog is 1.1.2.3.5.7, let's say. But something that is related to a dog, which is, let's say, a big dog, right? Now that will be very close in its situation. So that would be 1.2.4.1, maybe slight difference here and there. So while a computer does not understand the English, but the way these embeddings are stored, they are stored near each other, which is why the numbers do the job and the numbers give away the location of any particular storage, right? So of course, tougher concept. Good thing as a product manager, you don't need to implement it, but you need to know it, right? Because you're going to be in conversations with people where they are going to make this conversation, right? Now, of course, you can have three ways in which you can search. You can search by keyword, exact matches. Like I said, this is the older way. It's a little slower. It's great only when you've got like very precision data. Mostly you do semantic search where, the embeddings thing we just did, it catches whatever is intent and it's great for most natural question, right? So that is where it is. And then hybrid is of course where you run both. You try and understand that, okay, I'll search by keyword, I'll search by semantic, and then whichever is the best possible out of it, I'll show it. But the essential machine is to retrieve, chunk, embed, and search, right? Now, once we've done this, right? Once we've understood, how retrieval works, we've understood the overall. Let me just go back to this. We've understood that this is how it works, right? So your ingestion is all about chunking, which strategy to use to chunk, and then extraction is all about how you can map whatever is written in the question to a similar location to whatever was in the knowledge base. Now, once both of this is done, the next step is fairly easy, right? Why? Because in the next step, what happens is everything that got done here gets copy pasted and added to the prompt and gets sent to the LLM, right? Very straightforward way of doing it because, it's extremely simple, extremely logical, and you could go from there. Now, to showcase you the entire RAG pattern on how it works, we'll just close this with a live demo, right? So what I've done here is I have, created a simple artifact. What this does is we've created like a random product called Nimbus, right? And what we've done is we've just created certain questions, right? And we've tried to show what happens with and without RAG. So here what happens is first, let me run it. So with RAG, what happens is, okay, let us run and then you will understand it. So without RAG, what will happen is your question it will go straight to the model. The model is going to say that, hey, I don't have access to any internal Nimbus documents or policies or this. So I would recommend checking their website. This is what usually you would get from a chat GPT as well. So of course, not good enough. Now let's see what happens with RAG. Now with RAG, your question is broken down. It's turned into a vector. Now this is the number that I was talking about. Because your computer does not understand Nimbus, refund, all of that. So what happens is what is Nimbus's refund window is stored as a vector. This is the exact vector that it is stored at 0.18, 0.72, 0.05, 0.91, 0.03. So this is the vector that it gets stored at. Then the knowledge base is searched with this vector itself, right? So you get some matches, you get a match for refund policy, you get a match for pricing, and there the top K happens, which is you got all of these relevant similar places, similar to wherever the question was, and then you ranked them and you figured out that, hey, maybe refund policy and pricing are two good options to send based on this retrieval augmented generation. So that is where you go ahead and add those sources to the prompt. So you added the refund policy to the prompt, you added the pricing to the prompt, and then the answers got grounded in this entire source because now the AI bot has the data to this and it's also got the data of what the plans are, right? And that's based on that it's going to generate this, right? If let's say when was Nimbus founded, and if I run this again, now again, if you're doing it without it, it might not have the answer. So it would say that here again, it would search the knowledge base. This time, there will be a different vector because while Nimbus might be the same as last one, but the other words would be different. So it's stored there. Then what would happen is, company history and pricing are going to be two highest. Company history is going to be 0.99 because that's the most relevant. And then based on that, your answer gets generated accordingly, right? So that is basically how a RAG system or how a RAG pipeline functions. Now, to build this, you don't need to be the one who actually builds each of these ecosystems. So you don't need to be the one who builds this. There are, ready-made tools that provide embedding models, just like you have large language models, you have embedding models. Those embedding models turn this, all you need to do is you need to give this text to that embedding model. It's going to turn it to a vector, store it into a vector database. Then the search is also something that the vector database would give it. And then, adding it to it would also work out. So you don't have to implement all of this, but yes, without this knowledge, you're going to implement, a weaker version of RAG, and that's probably not what you would like to do, or that's probably not what you would want to have, right? So that is basically how RAG is. Just to close, there is just one more thing which I would cover, which is where is RAG heading right now, right? What are the different versions, right? So of course, there are three patterns that are here, right? If you want to understand where the entire RAG ecosystem is there. So there is simple RAG, retrieve, add it and answer. This is your starting point, perfect for your prototyping and all of that, but not great for production. The next is RAG with memory, which is to add a memory layer so that it remembers the conversations and has a follow up. Then you got something called as branched RAG, where one question is broken down into three. Each of them is embedded. Each of them is searched with chunks, and then you get a better answer. Then you've got HYDE or hide, which basically what happens is the model drafts an answer. It drafts a fake answer just based on the context given to it, and then that answer is used to search the knowledge base to find whatever chunks were relevant to them. It's gotten a better outcome than you manually chunking it. And then adaptive is where your system decides which RAG to use, whether it used to needs to do a simple one, needs to use branched RAG, needs to use hide, or needs to just go ahead and not use RAG at all and answer it via an LLM. Now, of course, we dive deeper into all of this when we study for RAG in our program. But for this community live, I hope this gave you the understanding of what RAG is or how RAG works. And of course, there is a small spec worksheet for you, which will be added with the YouTube video that we are going to post. But I'm just going to drop the link of it as well here so that you have an understanding. So what does this does? This basically is your cheat sheet, right? So what feature are you building, right? Do you even need RAG? Then what is your knowledge base? How will you chunk it? How will you search? What is the pattern that you're going to use? And then quality gate. I mean, of course, we didn't cover it because it's more detailed. We don't usually cover it in this community live. But basically, what's a quality gate? Do you want to have corrective RAG or self RAG? And how will you measure it, right? So this is basically your cheat sheet based on which your RAG spec gets created. And that spec is what you can send to your engineer, to whoever is implementing it, and send it from there, right? So if I just start putting data here, I just put selecting here, whatever it is, I just copy it and then send it to my engineer, right? There is a worked example as well here for you to see what it is, so that you have your cheat sheet of your checklist of everything that you need to do with RAG, and then just give it off to an engineer who is going to implement all of this. Right. So that is all I had for this community live. I hope you're liking these sessions that we do for our WhatsApp community, and yeah, hope that was helpful. I will see you guys again next week, hopefully, and we're going to pick up a smaller topic and try to break it down from a PM lens or from a generic professional lens. So thank you so much for joining. I hope this was helpful, and I'll see you next time.